I'm talking about some joint work with Jason Pearl, who is in the audience as well, who was a second-year undergraduate student here at Griffith when we did the bulk of this work. I want to motivate the work by telling you a nice little partial success story about Bell nonlocality. I like it that we're finally coming to a resolution of what I call the easy problem of Bell, which is the problem of giving a faithful causal explanation of quantum correlations that satisfies relativistic causality. This is achieved by the program of quantum causal models. So in today's talks, I won't focus so much on what I call the hard problem, which is related to the measurement problem, and it's another topic I've been talking a lot about lately. But then I'll point out that this resolution does not help at all with contextuality, even though Bell nonlocality is often said to be nothing but a special case of Kochen-Specker contextuality. Now, part of the reason this is not seen as a problem is that despite these superficial similarities between Bell nonlocality and Kochen-Specker contextuality, the foundational motivation has been historically very different. So the main result I'll present here is to rederive Kochen-Specker contextuality as a violation of classical causality, analogously as for the case of Bell nonlocality. And the upshot is that contextuality, I'll argue, also cries for a faithful causal explanation. And I think trying to achieve that will help us understand this phenomenon better and how it differs from Bell nonlocality. Okay, so these are the two papers this talk refers to. The most recent one is this one with my student Jason Pearl, which generalizes this earlier paper by myself. Not only that, but also it identifies an important implicit assumption that I made in that first work, and thanks to Matt Jones, who is in the audience, for pointing that out in on the first page of this paper. Great comments on that. I'd also note that Matt's presenting some work that I think is related to this topic as well, and I look forward to seeing it. So that is a subtle, then represents a subtle but important difference between the assumptions needed to derive our main result for Bell versus Kochen-Specker scenarios. And as a motivation, let me start with this quote from Bell, which I must admit I use in almost every talk. For me, then, this is the real problem with quantum theory, the apparently essential conflict between any sharp formulation and fundamental relativity. It may be that a real synthesis requires not just technical developments, but radical conceptual renewal. And here I take the point of view that at least part of that conceptual renewal regards our understanding of causality. And although that may be obvious in the case of Bell, I will argue that is also true of contextuality. Bell's theorem, of course, is best understood as being about a violation of the constraints from causal structure to possible correlations among events, and relativity comes in just to supply the causal structure. But the point of this talk is to say that we don't need relativity to find a reason to suspect our classical notions of causality, and furthermore, there is a path to resolve the issue. So let me start by defining our notation for a measurement scenario. We have a set of measurements, M1 to MK, with corresponding a set of measurement outcomes, and we take them to be the same set for all measurements without loss of generality. The compatibility structure defines the measurement context. So a pair of measurements is compatible if and only if it is in this set, which is a set of subsets of the set of measurements. A special class of measurement scenarios, or contextuality scenarios, are the Bell scenario. So here is an n-pi-type Bell scenario, where the set of measurements can be decomposed into n disjoint subsets, such that each context contains exactly one element from each subset. And what we call a Kochen-Specker scenario is just any scenario that is not a Bell scenario. And given a measurement scenario, an experimental test, an actual run of an experiment, consists of choosing a set of measurements to perform a particular run, so n measurements of a particular run, and with the constraints that they must form a context. And they have associated measurement outcomes that we denote by capital A, and they form measurement outcome pairs in the usual way. So just some examples. A Bell CHSA scenario is of this form. The measurements X and Y chosen by Alice and Bob come from two disjoint subsets. The outcomes You can take them to be the same set of outcomes, -1 and 1, and the set of contexts are the Cartesian product of the sets of measurement by Allison, by Paul. Kochen-Specker scenario, this notable scenario, an example of that is the Specker's triangle scenario. It's a simple one that contains 3 measurements with dichotomic outcomes, and the set of contexts. There's 3 contexts, M1 and 2, M2 and 3, and 1 and 3. And so in a particular run, in a particular test, the variables x, y are constrained to form a context. It could be a realization, say, in a sequential scenario, or it could be a joint measurability scenario. We don't make any particular assumption about how it's realized, just that the measurements form a context. And of course, that's generalized for arbitrary numbers of measurements. Now, what is the relationship between Kochen-Specker contextuality and Bell nonlocality? They're both violations of this mathematical condition of factorizability, whereby there exists a model of this mathematical form that reproduces the observable phenomena. This uses curly P to represent the observable probabilities and the normal P to represent model probabilities. And the second line here is a requirement that if a measurement occurs associated with more than one test variable, for example, if it appears in different positions in a sequential contextuality scenario, then the probabilities assigned by the model do not depend on the position in which this measurement occurs, whenever these are defined. And the fine Abramsky-Brenneberger theorem says that a phenomenon has a factorizable model if and only if it has a Kochen-Specker non-contextual model. And by Kochen-Specker non-contextual model, I mean a model that satisfies these 3 assumptions. Measurement non-contextuality, defined the usual way, that the probability for the outcomes of a measurement assigned by the model do not depend on the context in which it is measured. Outcome determinism, that the outcomes of a measurement are determined by a full specification of the variables in the model. And freedom of choice, that the measurements can be chosen independently of the variables. And Bell's original 1964 theorem also uses an analogous set of assumptions, what then Bell called locality, which Shimony called primary independence, which is weaker than local causality, outcome determinism, and freedom of choice. And primary independence or locality can be thought of as just a special case, indeed, of measurement non-contextuality, where the context for the measurement is, for local measurement, is the distant choice of measurement. However, primary independence is also motivated by relativistic causality. And what is the motivation for measurement non-contextuality in Kochen-Specker scenarios, those which cannot be performed with space-like separation, which cannot be factorized into disjoint subsets? In 2005, Rob Speckins, where he introduced his generalized notion of non-contextuality, he argued that it's motivated, that measurement of contextuality, as well as analogous notions for preparations and transformations, is motivated by Leibniz's principle of the identity of indiscernibles. I don't think he used precisely those words then, but he has more recently, which is not to be thought of as a physical principle as such, but a methodological principle, like Occam's razor, a type of inference to the best explanation. So if there are 2 operationally equivalent ontological theories, one of which satisfies Leibniz's principle and the other doesn't, then we should prefer the one that does. And in another recent paper, this one here, he argued more extensively and quite convincingly, in my opinion, that this principle can be thought of as the methodological principle underlying Einstein's principle of relativity and of equivalence. So in other words, it captures the spirit of relativity. And he also argued in this 2005 paper that outcome determinism, on the other hand, is not justified for unsharp measurements, and that calls into question the implication or violations of Kochen-Specker inequalities for non-idealized experiments. And indeed, isn't quantum mechanics supposed to be deterministic anyway? One could say, if measurement on contextuality has such a high pedigree, why would we take the violation of Kochen-Specker inequalities to imply contextuality when it would seem to be much simpler to reject outcome determinism? So what's the analogous argument in the case of Bell? So here in the following slides, I'll draw in some discussions from in this paper with Howard Wiseman. However, I'm using different terminology to match the more standard terminology in discussions of contextuality. So Bell's 1964 theorem then could be resolved in much the same way. Let's reject outcome determinism. And the problem with that is that in 1976, Bell showed that that was not enough because he could derive these inequalities from a weaker assumption, local causality, without introducing outcome determinism. And its assumption that if you have two space-like separated sets of events and they're correlated, then there must be some set of events in their common causal past, such that conditioning on that eliminates the correlation. And so do you reject local causality then in light of violation of Bell inequalities? And the problem for Bell was that local causality, in his opinion, captured a fundamental requirement of relativistic causality. He said, do we then have to fall back on no signaling fast and light as the expression of the fundamental causal structure of a contemporary theoretical physics? This is hard for me to accept. For one thing, we have lost the idea that correlations can be explained, or at least this idea awaits reformulation. So what does it mean to explain correlations causally? Bell's local causality can be traced back to Reichenbach's principle of common cause, which you can see is much the same as Bell's local causality, except that he doesn't require the common causes to be in the intersection of the path-like currents. So if we now add this assumption of relativistic causality, that the causal path of an event is in the path-like current, then that together with Reichenbach's principle implies local causality. So now we have a choice of rejecting one of these three assumptions in light of the violations of Bell inequalities. So do you reject relativistic causality? Say this, what is done in Bohr mechanics. And I think one of the reasons why it is an unpopular alternative for most physicists is that it violates at a fundamentally hidden level some operational symmetries in the phenomenon. So in other words, it also goes against Leibniz's principle. But perhaps we can't keep Leibniz's principle after all. But I think we should not give up without trying. So the question is, can we keep it? So what about Reichenbach's principle of common cause? In more modern terms, it can be seen as a special case of a principle of the classical causal models framework, for example, as formalized by Pearl, where causal structure is represented by a directed acyclic graph. And this is the DAG for a Bell scenario, the canonical DAG for a Bell scenario, which encodes cause and effect relations between the various variables. And one of the things that is implied by the graph are constraints on probability distributions that are compatible with the graph through the causal Markov condition, which says that a variable is independent of its non-effects given its direct causes. And the causal Markov condition implies Reichenbach's principle as a special case. So do you reject Reichenbach's principle and thereby reject the classical causal model framework? But if you do that, then what about causal explanation, and what about the various applications of this framework? In 2014, Ray Lau and I proposed to break Reichenbach's principle into two independent principles: the principle of common cause as such, and the principle of decorrelating explanation that we at the time called the factorization of probabilities, which the common causes requires that correlations need to be explained causally. And the correlating explanation says that what it means to explain correlations causally is that conditioning on the common cause, the correlations are factorized, it eliminates the correlation. So the conjunction of these two imply Reichenbach's principle of common cause. And we also propose in that work that if we use the Liefers-Becker's quantum conditional states formalism, this principle of the correlating explanation could be substituted by a factorization of quantum channels of the Choi-Jankowski isomorphic operators to the quantum channels in a Bell scenario. And that is essentially the kind of resolution of Bell's theorem that is achieved by the program of quantum causal models, of which this is an incomplete list of contributions. There's a lot of work being done on this in recent years. And the key features of these, and these of course go well beyond that simple proposal that we had in 2014. And the key features of these is that they allow for causal discovery, for example, as shown by Cristina Giamazzi and Fabio Costa, following a framework by Fabio and Sarah Shrapnel. It's compatible with relativistic causality, reduces to classical causal models as a special case, and it provides a faithful causal explanation of Bell correlations. So it's very interesting developments, which provides at least a partial resolution of the puzzle of Bell's theorem, what is called the easy problem of Bell, which is the problem of giving a causal explanation of Bell correlations. It's a candidate causal explanation. You may not believe that it's the correct one, the true one, but it's a candidate causal explanation. It generalizes the classical case and accommodates correlations. Now, what about contextuality? So that's a nice story. But what about contextuality? In general, contextuality scenarios, the causal structure isn't constrained by relativistic causality. So here we take a different approach. We show that all possible causal structures that can explain contextuality must violate a fundamental causal principle, the principle of no fine-tuning. So Leibniz's principle, again, together with the causal models formalism, motivates the principle of causal no fine-tuning or causal faithfulness, which requires that every conditional independence between variables should arise as a consequence of the graph, of the causal graph, and not due to special choices of model parameters. So, for example, if you can't send signals faster than light, then we shouldn't prefer a theory that has superluminal causation, because the only way that this theory could reproduce the operational observation, the independence between distant outcomes and the between outcome and the distant choice of setting is through some fine-tuned choices of the model parameters, the fine-tuned distributions of hidden variables. So in the notation of causal models, this is translated in this way. If variable b is independent of x given y, then b must be disseparated from x given y. So this is b independent of x given y, then it must be disseparated from x given y, and this disseparation is a graphical criterion. If you're interested in the technical details, stay tuned for Jason's talk that's coming up just after mine. So why do I say this is motivated by Leibniz's principle? Well, first because without assuming causal faithfulness, it's not possible in general to discover the causal structure associated with a given phenomenon, which means that there would be in general two or more ontologically distinct causal structures that are empirically equivalent. For example, in biomechanics, there would be a preferred reference frame in which the superluminal causation occurs, which cannot be discovered empirically. So could there be some faithful causal model that can explain Bell correlations, even though not the canonical relativistic causal model? And in 2015, Chris Wood and Rob Speckens answered this question in the negative. They showed that no classical causal model can explain all instances of bipartite Bell nonlocality without causal fine-tuning. So what do they prove exactly? They start from the following three assumptions that I'm calling choice independence, that the choices of setting are independent of each other. Local setting dependence, that the local setting is statistically dependent on the local outcome is dependent on the local setting. It's not the case that they are independent. And no signaling, that say B is independent of X given Y and vice versa, A is independent of Y given X. And then also assuming causal no fine-tuning, they show that these four assumptions imply factorizability, imply Bell inequalities. Now, in this 2018 paper, the one that I mentioned in the beginning, I show that the same conclusion holds without requiring the first two assumptions. There is just assuming no signaling and causal no fine-tuning alone was sufficient to derive Bell inequalities. In other words, no classical causal model can reproduce the violations of bipartite Bell inequalities without fine-tuning. And because this proof does not assume choice independence, then it opens the door for a generalization to Kochen-Specker non-contextuality. Why does that matter? because what is important, because in Kochen-Specker scenarios, in general Kochen-Specker scenarios, the choices are dependent. They have to form a context. So just bringing the some illustration of these scenarios. So now note that this is not necessarily a violation of the usual freedom of choice assumption. So if you take the canonical causal model for a Bell scenario and you just make the choice of setting being dependent, chosen by some say, choice of context, then that's essentially a canonical causal model for a Kochen-Specker scenario. It's a model of this form. Now, a graph of this type still implies factorizability for Bell scenarios. What is important is not that the choices of setting are independent of each other, but that they are independent of the hidden variables. And in this case, they are still independent of the hidden variables. So this, if you apply the causal Markov condition here, you still get the usual factorizability condition for Bell scenarios. You still get a Bell inequality. In other words, you can't violate a Bell inequality by making the choice of setting being dependent of each other, as long as they are not also dependent on the hidden variables. But unfortunately, that is not enough for Kochen-Specker scenario. And thanks for Matt Jones for pointing this out after reading an early version of my paper with Jason. So because measurements may appear associated with different variables in a Kochen-Specker scenario, for example, in a sequential scenario, they may appear in different orders. So we also need to require, when we express the condition of factorizability in terms of an experimental test in this way, we also need to require that the response function of the model for each measurement does not depend on the order in which it appears. It's usually just implicitly assumed when one writes a factorizability condition for a contextuality scenario. But that's because usually one is not trying to be explicit about the operational variables that those measurements are defined relative to. One's usually just treating the measurements as abstractions. So that's an important condition as well. So for contextuality scenarios, then we need a stronger notion of no fine-tuning, which is the following. Causal model satisfies what we now call no fine-tuning, or it's faithful relative to a phenomenon P, if and only if it satisfies what previously called no fine-tuning, but now I'm calling this causal no fine-tuning, following the terminology from this paper from Catani and Lifa, which is just the recognition dependence which arises as a consequence of the causal graph, and a notion of operational no fine-tuning, which is that the operational symmetries in the phenomenon must be reflected in the model rather than holding only for special values of the model parameters. And the only implication of this operational no fine-tuning assumption that we need, in fact, is that the outcome statistics of a measurement do not depend on the variable it's associated with. So, or rather, if the outcome statistics do not depend on what variable is associated with, say the probability for a measurement M, for the outcomes of measurement M, are the same whether it's associated with some variable I, label I, or a variable with a label J, then the model should satisfy the same symmetry. In particular, if the model has a factorizable form, then these response functions should be the same regardless of whether the measurement is associated with I or with J. So if this is analogous to this notion of operational no fine-tuning that was recently introduced by Catani and Lifa in this paper, but it's weaker than that. We don't require as much as it was the visual. And it also follows from, but it's also weaker than Speckrum's notion of measurement non-contextuality, since it only requires that the response function is independent of one particular feature of the context, which slot in this process the measurements appearing in. This particular assumption is not assuming that it's also independent of what the other measurements have been performed. It's weaker than measurement contextuality. But it's quite clearly also implied by Leibniz's principle, just as the same say as measurement of contextuality itself. Okay, so finally now considering an arbitrary contextuality scenarios with an arbitrary number of measurements per context, or an arbitrary number of variables in the measurement test. We use this more general notion of no disturbance that generalizes no signaling. The probabilities for any subset of outcomes depends only on the associated subset of settings, and the marginals for the same measurements are independent of the variable index. And these are just properties of the phenomenon, which you can just go to the lab and verify that some particular phenomenon satisfying these properties, then satisfies no disturbance. So say, for example, one usually requires repeatability, then an assumption property like this would be satisfied. And so we arrive at main results with that every phenomenon satisfying no disturbance in an arbitrary contextuality scenario that has a faithful causal model is factorizable. In other words, no fine-tuning and no disturbance imply factorizability in arbitrary Bell-Kochen-Specker scenarios. Wrapping up. Now all the details, all the technical details would be in Jason's talk. I'm just discussing the conceptual motivation and just an outline of the result. So non-contextuality and Bell locality both arise from the requirement of no fine-tuning on classical causal models. So it unifies Kochen-Specker non-contextuality and Bell locality as violations of classical causality, at least an important assumption of the framework of classical causality, of the framework of causality in general, but as applied to the classical framework in particular, because of assuming the causal Markov condition. And we don't assume, we make no assumption of determinism as the original Kochen-Specker non-contextuality assumption, or the original Bell 1964 theorem, and it's a theory-independent derivation. Now, this finally creates an open problem. So, like I was saying before, quantum causal models give a faithful causal explanation of Bell correlations, but not yet of contextuality. And I think this is an odd situation, because the overarching argument in this talk is that Leibniz's principle begs for a faithful explanation of correlations if one exists. And until recently, it was thought that it was not possible to give a faithful causal explanation of Bell correlations, but now we have found a candidate explanations through some suitable generalization of the classical causal model formalism. And why not for contextuality as well, if it's also a violation of classical causality analogous to Bell locality? I think that
Eric, you've got 2 minutes.
Okay, just finalizing then, I think finding such a model, if it exists, would be very helpful in better understanding the nature of contextuality and how it differs from Bell locality. Thank you.
Sorry, you'd like a better setup. Yeah, so I was wondering about, you said that your no fine-tuning principle is weaker than measurement non-contextuality. But if you had two different measurements,
the operational no fine-tuning part of it.
Yes.
Yeah.
If you had two different measurements that gave the same statistics for everything, why wouldn't that qualify as an operational symmetry?
Well, the things that I'm saying that it's not for everything. In measurement non-contextuality, we are assuming more. We're assuming that if two measurements are the statistics are independent of the context, then they have the same response functions. Here, I'm not necessarily assuming that they have statistics which are independent of the context, just a particular aspect of the context. So it's implied by measurement non-contextuality, but I'm not using other things which are also implied by measurement non-contextuality in that assumption.
Thanks.
So you're just kind of by fiat only applying the principle to that.
By fiat, I'm just only applying that to the particular case. That's right. I'm saying the only implication that I need for the proof is a very small part of the implication of measurement non-contextuality.
Thanks.